All right, welcome back to another episode of Science with Surbeck. Today what we're going to do is we're going to review ions, ionic compounds, and then be able to name some of those ionic compounds. So a couple of objectives I want you to be able to accomplish is to be able to define the terms ion, ionic bonds, and ionic compounds, understand the guidelines for naming and writing the formula of ionic compounds, and then also be able to write the names given the formula of certain ionic compounds. So let's first start out here with what is an ion. And an ion is defined as atoms or a bonded group of atoms with a positive or negative charge. And so there's two different kind of ions that we need to be aware of. One is a cation, and these are defined as positively charged ions. And now these positively charged ions, they have this positive charge because they lost electrons, or they gave away electrons. Now the other type of ion we have to be aware of is an anion. And an anion is defined as a negatively charged ion. And they became negatively charged because they gained an electron or electrons. And so with those things in mind, we can get into the definition of what an ionic bond is. So an ionic bond is defined as an electrostatic force that holds oppositely charged particles together in an ionic compound. Now, these ionic bonds are going to form during multiple types of chemical reactions. And then our last definition that we have here is an ionic compound. And an ionic compound is defined as any compound that contains ionic bonds. So the big takeaway here, ions, they either gained or lost an electrons, and they become either positively or negatively charged. We can classify those as cations or anions, and then the ionic bond has to form during a chemical reaction, and as a result, we obtain or produce an ionic compound. So now what I want to shift gears to is actually understanding how we write the formulas for ionic compounds. So we'll transfer to the next page here, and we'll go to the ionic formula guidelines. So when we write the formulas for our ionic compounds, the first thing that we have to have is that the symbol of the cation or the positive ion is always going to be written first. The second thing is that the symbol of the anion or the negative ion is always written second. And then the third thing is that if needed, we must include subscripts, which are small numbers to the lower right of our chemical symbols. Now, these subscripts are used to represent the number of ions of each element in an ionic compound. And then we need to be aware that if no subscript is written, it is assumed to be 1, or the number of ions present in the formula is assumed to be 1. Okay, so if we put these things to the test, we can find out what is the correct ionic formula between potassium and oxygen. And before we even get into details with this, what I'm going to do, I have a blank periodic table on the next page of notes, and what I want you to do is this. I want you to follow along, and I want you to write exactly what I write. So this right here that I'm about to write becomes the charge that each group of element obtains when they become an ion. So this first group, when it becomes an ion, it loses 1 electron and it forms a positive 1 charge. So every element from hydrogen all the way down to francium, when it forms an ion, has a positive 1 charge. Now, if we transition here to beryllium all the way down to radium, this entire group has a +2 charge. Now we're going to skip over the transition and the intertransition metals, and we're going to move to the group boron all the way through thallium and element 113. This group of elements forms a +3 charge. We move over to carbon all the way down to element 114, and we have to be careful because this is either a plus or -4. Now, the way we typically know if it is a plus or minus is if it is written second or first will determine if it's plus or minus. The group with nitrogen all the way down to the group here has a -3 charge. Group with oxygen all the way down has a -2 charge. And then the group with fluorine all the way down has a -1 charge. So the noble gases have a charge of 0, so that is something to note. So you can put this on your periodic table, and I would encourage you to do that. Or if you need a little extra help, what I've also attached in notes is the ion formula chart. So this right here tells us what is the charge of our most typical ions, and it includes a lot of elements that are found on the periodic table. Now, one thing that I have skipped over is the transition and intertransition metals, and that's because they have a varying number of electrons that are lost. So some elements actually have a couple different what we call oxidation states or charges. So anyways, let's go through this and get back to our example. So we want to find the correct formula between potassium and oxygen. So potassium, if we find potassium on the periodic table, it has the element symbol K. So I'm going to first write K down. And I also want to look up what is the charge. And so K is in that first group. It has a charge of 1+. And then I move on to oxygen. And again, same thing. I find the symbol for oxygen to be O. And so I write down O. And the symbol for oxygen is a 2-, or the charge is 2-. Now, this is really important because I really didn't describe it in the directions, but when we do this, what we have to do, we have to cross the charge number, we have to swoop it, and that becomes the subscript for the other element. So for example, we always start here with our negatively charged ion, and we swoop it over, and so this means that we need 2 Ks. So we have K2, and we do the same thing over here with potassium. We take the charge and we swoop it to make it the number of ions we need of that element. Now I'm going to use purple so we don't get confused here, but we need 1 O. Now, to emphasize this, I'm going to write K2O1. If we look at our rules, it says, hey, no subscript written. We assume it to be 1. So what this formula becomes is K2O. Now, notice this. Notice this. I wrote the positively charged ion, the cation first, which was potassium, followed by the negatively charged ion or the anion. That is really important as we move forward. So again, remember the periodic table, remember that ion formula chart to help you understand those charges of those elements. So now what we are going to move on to is just doing the reverse process, and that is going from the polyatomic ions, which add another little extra rule into our particular set of circumstances here. So we'll transition here and we'll go to polyatomic ion formula writing. So with our polyatomic ion formula writing, the first thing to remember, poly is many atoms that make up an ion, and I'll show you that here in a second. But for this particular changes here is this: the charge is given to a polyatomic ion that is going to apply to the entire group of atoms. So I added there just the definition of polyatomic ion, and then I just stated the charge of the given polyatomic ion applies to the entire group of atoms. So let's take example here, our PO4, which is phosphate, and it has a charge of 3-. This charge of 3-, so I'm going to say 3- charge, applies to PO4 as a group. Now another thing to note is that the entire polyatomic ion is acting as one single ion or one single unit. The other thing that is really important, major difference here between polyatomic and normal atoms, is this: the subscript of the atoms within the polyatomic ion are never changed. So if you need more than one of those polyatomic ions, you place parentheses around that ion and write the appropriate subscript outside the parentheses. Again, if more than one polyatomic ion is needed, place parentheses around and write the subscript outside of these parentheses. So we'll do this in this example. So now we want to know what the formula for the compound form between the calcium ion and the phosphate ion. So calcium is an individual element, and so if we take our periodic table that we just labeled and we find calcium, element 20, calcium has the symbol Ca. And what you could also notice is that if you went up that column, calcium has a charge of +2, and we're going to write it as 2+. Now, phosphate, you could look on the periodic table, but I'm going to save you some time here. It is not on the periodic table. It is a polyatomic ion. Now, to help you out here, I do have another chart that lists some common polyatomic ions. And if you look on the 3- charge, you will find phosphate. And it's hard to see here on the computer here, but phosphate has the formula PO4 with a charge of 3-. So again, PO4 with a charge of 3-. Now what we're going to do the swoop de loop here, and so the charge number becomes the subscript for that opposite ion. So the charge number of PO4 is 3. So again, you do your swoop de loop here. That means we need 3 calcium ions. So we just write Ca 3, and I want to point out this. Because calcium is an individual element, we do not need parentheses. Now, if we go over here and we try to find how many PO4s we need, what we do is we take that charge number, and again, we do the swoop de loop, and I'm going to put way outside here. So this means that we need 2 PO4s. So to write that formula correctly, because we need 2 PO4s, we put in parentheses PO4. Notice how that is the same formula, and because we need multiple of these phosphates or these PO4, what we do is we put outside the parentheses a subscript of 2. And we did that because we needed more than one of these PO4s. Now, again, always double check here. Your calcium, or excuse me, your positive ion, which is calcium, should be written first, followed by your negative ion, and this is how we should write it. Now again, parentheses, only because this is polyatomic and we needed more than one. So this would become our formula for a calcium and phosphate ion. Again, that helps you out there. Those charts help you orientate things correctly. Now what we are going to do is we are going to transition to go from formulas to actual names. So now we'll have formulas and names in our video here. So, naming ionic compounds. Our guidelines here is this. Number one, the cation, or the positive ion, is always named first, and then the name of the anion, or negative ion, is given second. Now, the second thing that we need to get to is naming the cation. So, if we are working with an element, we strictly use the element name. So, an example here is sodium. So, if we have sodium and it's written as Na in our formula, what we would do, because it is an element name, we would just look up what it is on the periodic table, and we would find out that the name would be sodium. And all we have to do is write that name down. That's what the cation would become. Now there's one exception, and that is this. If the cation is a transition metal, the charge must be indicated in a set of parentheses. So an example of this would be iron 3+. So iron 3+, how it would be shown is Fe3+, and so it is a transition metal, and so what we have to think about is we write the name down, iron, but we also have to include the charge of this transition metal, and we do this by putting a set of parentheses, and then we have to indicate these in Roman numerals. So because it has a 3+ charge, the Roman numerals would be 3 lines, and so that would be iron 3+. Now we get to naming the anion. So the first thing with the anion is you're going to use the root of the element name. And then what you have to do is you have to chop off the ending and make it an IDE ending instead of the original element name. So let's go through an example here with naming an anion, and let's use the element Cl. So we have Cl, it's in the formula, it's listed second because it is an anion. And the first thing that we do is we look up our element name. So the element name for Cl is chlorine, and so all I'm going to do is write down chlorine exactly how I see it on the periodic table. Now, we need to chop off the ending so that we can put on the IDE ending. So what we do, and it's different for each and every element, but typically the last few letters, the last 3 letters sometimes, we chop off and we tack in IDE. So when we rewrite this particular name of this anion, it becomes chloride. Now, the final thing that we have to do is if the compound contains a polyatomic ion, we are just simply going to use the name that is given for that polyatomic ion. So an example of this would be if we came to the cation NH4+. Again, it's polyatomic because this whole set of atoms has that single charge. And to help you out here, all you need to do, one of the help sheets that I've given you here is you find NH4 and you write down the name exactly how you see it on one of these charts. So the name here for NH4 becomes ammonium. Now another example here would be something like OH minus. So again, another example would be OH minus. And if you would come to the chart, you would find OH minus, and OH minus, the name of that is hydroxide. And again, you just write down the name that you see listed here. So this would become hydroxide. We don't change any endings because it's polyatomic. So let's go ahead, let's put this to the test, and let's name some of these compounds. And that's what I have on the next sheet of paper. So we have NaBr as our first element that we need to name. So the first thing that we do is we identify what is Na. So if you find Na, it's element 11, and the name of that is sodium. Now the rules for naming the first element, or the cation, is always just write this down. So I'm going to draw a line that this is sodium. And then we have to ask ourselves, is sodium a transition metal? Does it span in this box or an intertransition metal? Answer to that is no. So we don't have to worry about the charges. Now, what we have to do here is this. We have to now look up Br because that is our next element listed. So Br has the name of bromine. Now, bromine is the second element listed. So we have to modify the ending because it is a anion, and so we chop off the ending and we add IDE. So for NaBr, when we go to name it, I'm going to name it out to the right here, it becomes sodium bromide. And that is the name for NaBr. Now we get to KOH. So the first thing here is you need to identify what is the positive and negative thing. And I will tell you that under most circumstances, the only polyatomic ion that we commonly deal with is ammonium. So if it's not ammonium, that means there's only a single element. So I'm going to help you out here, and I'm going to divide K and OH. So we look up K. And so K, if you find it on the periodic table, is the element for potassium. And so all I'm going to do is write down potassium. Again, we do not need to modify the ending, but we also need to ask ourselves, is K a transition metal? Is it found in this block of 10 or block of 14? The answer to that is no, so we can move on. Now, OH. There are multiple atoms in OH. That means it's polyatomic. So it's really nice for us. We just find OH, and the name of OH is hydroxide. So out to the side here, I'm just going to write down hydroxide. And because it's polyatomic, we do not have to modify that. We can leave it exactly how we found it on the sheet. So out to the right here again, I'm going to write down KOH's name, which is potassium hydroxide. And it's as simple as that. Now we come down here to our third example, and that is CuNO3 2. So the first thing here, that should be a dead giveaway that I know where my polyatomic ion is. That's because it's in parentheses. So what we do here, that's a dead giveaway. You can make your dividing line right there. We need to look up what is the element Cu. So we look for Cu. The element is copper. And then the second question that we have to ask ourselves is this: is copper one of those transition elements in these middle blocks? The answer is yes. It is right smack in that middle. And so what that means is we are going to have to indicate the charge in parentheses for copper. So what I'm going to do to help us out is I'm just going to leave a blank set of parentheses, and then we'll get back to this. Now, we have NO3, and we have two of those. And so our NO3, because it's polyatomic, all you need to do is you need to look up on our particular sheet, and you need to find, well, what is the charge for our NO3? Well, NO3 has a 1- charge, and the name of that is nitrate. So again, because the name is nitrate and it's polyatomic, it's really nice. All we need to do is write down nitrate. Now, we're not quite done because I said we have to decide what is the charge of this copper ion involved in this particular formula. So what we do is this. For our copper, we pretend that this is like a variable in math. And so I'm going to call my copper an X. And then we have to add to it the total charge of NO3. So the way we do this first is we identify how many NO3s do we have. So we have 2 times the charge of NO3. So the charge of NO3 is a 1-. That's what our chart says. So we take 2, which is the number of NO3s, times -1, and then remember this: all ionic compounds have to have an overall charge of 0. Okay? So we set this equal to 0. Now what I'm going to do is I'm going to have X plus 2 times -1 is -2 equals 0. And so if we consolidate, X minus 2 equals 0. We move this 2 over, we add 2. Our X becomes a positive 2, which what this means is that this is the charge of copper. So what we can do in parentheses is we can insert the charge of copper to be a Roman numeral of 2. So when we go to rewrite this, and I'm going to write it below, the name of CuNO3 is copper 2 in parentheses, and then nitrate. Okay, so now we have one left. We have Ag2 Cr O4. And so for this, we first again identify where is our positive from our negative. And again, I'm going to help you out here. If it's not NH4+, it's probably just a single element. So we have Ag2. So we look up Ag on our periodic table and we find it, and the name of Ag is silver. So we have silver, and then we ask ourselves, is it one of these elements in the middle? Yes, but I want you to hold tight. There are 2 elements that we do not give a set of parentheses to if it's in the middle. So I want you to write this on your periodic table. The first element that we do not give a set of parentheses to is silver. So you can put no parentheses for charge. It is always going to be for Ag. Ag is always a 1 plus charge. Always. The other element that we do not put a set of parentheses for in our transition metals is zinc. Zinc, again, no parentheses to indicate that charge. Zinc, when it is in its ionic form, it always has a 2 plus charge, and so that is why we never have to indicate what the charge is of zinc and silver. So yes, these are transition metals, but we do not need to indicate in parentheses what the charge is. So that's really nice for us. We don't have to worry about what the charge is. We don't have to deal with that parenthesis business like we did in that previous problem. The other thing is we have CrO4. Now, CrO4, we have to identify what that is, and because there's multiple atoms in that particular ion, we come over and we have CrO4, and you notice here that that is chromate. So the name of Ag2 Cr O4 is silver chromate. Again, there is no parentheses for silver because it always has a +1 charge. All right, so this concludes the review of ionic naming and formula writing. I hope you have enjoyed this video, and as always, subscribe. All right, welcome back to another episode of Science with Surbeck. Today what we're going to be talking about is covalent bonds and acids. So there's a couple of objectives that I want you to be able to accomplish by the end of this video. Number one is to be able to describe what a covalent compound is. Number two, name and write the formula to covalent compounds. Objective number three is to be able to know or define what an acid is, and also be able to write the formula and name an acid. So with a covalent bond here, a covalent bond is just defined as a chemical bond that results from sharing electrons. So very similar to the other type of bond, ionic bond, that we've talked about, but the big difference here is that they share those electrons. And so because they share electrons between two atoms, we have to keep in mind this. These shared electrons that are in a covalent chemical bond are considered to be part of the complete outer energy level, or we call that the complete octet of both atoms involved in that covalent bond. So again, because they share this, they are both accounting for those electrons in their outer energy level. And now these covalent bonds that occur in a or between two atoms are going to occur mainly between non-metallic atoms. So remember, with nonmetals, if we think back to the periodic table, they have this stair-step line, and anything to the right of the stair-step line is considered to be a nonmetal. Now don't forget about hydrogen. That element also sneaks in there as a nonmetal. Now, because, as we just saw, these covalent compounds involve mainly nonmetallic elements, these elements are going to be relatively close to each other on the periodic table. Okay, so now that we have an idea of what a covalent bond is, we can get in the details of how specifically we name these covalent compounds. So what we start out with is this: naming binary chemical covalent compounds. And I want to start out with what a binary covalent compound, or a molecule as we'll call it, is. Again, I'm going to use molecules or binary covalent compounds interchangeably, and that's because they both use covalent bonds. And so what it is, or what they are composed of two different nonmetals and do not contain metals or ions. So now what we have are these steps to name these binary molecules or these binary covalent compounds. And so the first step is to name the first element in the formula, and we do this by just looking at the name of the element on the periodic table, using that name, and we write the entire name of that element down. So again, all you got to do is look what element that is, write the name of that particular element down. The second thing that we do is name the second element in our compound. And so the second element in the formula is just named using the root of the element name, and then you change the ending to IDE. So remember, each element we're going to take a little bit different amount off and add that IDE ending, but the second element in a covalent compound is definitely always going to have that IDE ending. The third step, and this is where we differ for how we name covalent versus ionic compounds, but the third step to name a covalent compound is this: we need to use prefixes. And these prefixes indicate the number of atoms of each type that are present in the compound. Now, these prefixes I have in this particular chart. So it shows how many atoms of each element in that formula you have and what prefix that you need to use. Now, there is one exception to this, and that is if the first element in the formula, if it only has one atom, it never uses the prefix mono. Again, no mono prefix is used for that first element in that compound. Okay, so now what we can shift gears to is how exactly, in an example, would we name a particular covalent compound. So if we shift gears here, we will transform to our examples, and this first example is CCl4. Now, you may be wondering, well, how do I know if it's a covalent or ionic compound? Well, if we look up C and Cl, notice how they're both on the right-hand side, and they're both nonmetals. So that's that first indication. The next thing that I do is I divide the elements involved in the compound. So I have C and Cl4. Remember that capitalization indicates that start of that new element. And so the thing I need to do now is look up what is the name for that element C. I find it on the periodic table. That name of that element is carbon. Now my rules tell me just write down the name of that element. No modification is needed. The second thing that I need to do is I need to find out, well, what is Cl, or what is that name? And if we look here, the name of Cl is chlorine. Now our rule number 2 said the ending of this second element involved in the compound needs to be taken away and added IDE. Now, where that gets taken away is dependent upon each and every element. You chop a little bit more off for some elements rather than others. So what I'm going to do at this point is I'm going to write down carbon chloride, but I'm going to leave space because we still have to go back and we have to add our prefixes. Now, once we get to this point, what we do is this. We go back to the formula and we look how many elements are involved, or how many atoms of each element are involved. So you look at carbon, you look for the subscript. There is no subscript, which in chemistry, if there is no subscript, we assume there's just one. So if we looked on our prefix sheet, we notice the prefix for just having one of those carbon atoms is mono. But hold on, our exception to our rule said, hey, if it's the first element listed and there's only one of them, we do not put that prefix mono. So right here, we just leave it as carbon. So now we move on to our Cl. And always our second element listed will have a prefix. So we look at the subscript here, which is a subscript of 4. So that means we have 4 Cl atoms. And we look up the prefix for 4 Cl atoms is tetra. So in front of chloride, what we do is we add the prefix tetra. So this formula, CCl4, has the name of carbon tetrachloride. Now we move down to another example, P2O5. Again, the first thing that we need to do is we need to split the two elements that are involved in this particular compound. And we look on our periodic table and we find our P stands for phosphorus. Now because it's the first element listed, all we need to do is we need to write down the name of that element and no modification is needed. The second element, O, if you look on the periodic table, the element name is oxygen, so we write down oxygen and we have to chop off the ending and make it become IDE. Now, again, it's a little bit different for each and every element. We take a little bit more here off of oxygen, and it becomes oxide. So now, what we have here is this. We have our phosphorus oxide, which I'm just going to go ahead and rewrite. Remember to leave some spaces because we have to add prefixes. So I'm going to leave some big space in between each of those spaces. So now we look at phosphorus. The number of atoms is indicated by that subscript, so that is a 2. So you look on your prefix chart here. The prefix for 2 atoms is di. So in front of phosphorus, we tack on the prefix di. That becomes diphosphorus. Now, oxygen, we look at the elements or how many atoms of that particular element we have, and you see there's a 5. So again, we get our handy dandy chart out, and 5 atoms, 5 oxygen atoms becomes the prefix penta. So our formula becomes diphosphorus pentaoxide, or our name of our element. Now sometimes here, what you'll see, because the 2 vowels, they will modify that ending. So we'll often have just pentoxide, because pentaoxide, it's very difficult to say. But P2O5 is diphosphorus pentaoxide. What we are going to do now is we're going to transition from not only covalent compounds, but we're going to transition to acids. All right, so transitioning here to acids. So an acid, in this particular class, an acid is going to be defined as a compound that produces a hydrogen ion, H+, in solution. And to keep it simple, what we're going to do here is that any compound that we see hydrogen listed first, we are going to utilize the acid naming protocol and the acid naming formula writing. So again, as we have a hydrogen listed first, that's going to indicate that we have an acid. So there's two types of acids. The first type of acid is known as a binary acid. And a binary acid is defined as a molecule that contains hydrogen and one other element. Now, we may have multiples of this one other element, but again, it is just one additional element from the periodic table. Now, our other type of acid is an oxyacid. And an oxyacid is defined as a polyatomic ion that is combined with hydrogen. So depending on if we have a binary or oxyacid will determine how specifically we name our acids. So we'll start out with binary acids and then we'll shift gears to our oxyacids. So our steps here to name a binary acid is as follows. The first step is to use the root of the second element listed. The second step is to change the ending of the second element to IC or IC. And then the third step is to place the prefix hydro in front of the name of that second element. And then our fourth and final step to name a binary acid is to place the word acid after the second element is listed and named using that protocol above. Alright, so let's try some of these in a few examples. So we get down here, and yes, it is an example to name acids, but if I were to get to this in a particular problem, and you ask, okay, well, how do I know if it is an acid? Well, for us, we're going to keep it simple for right now, and anything with an H out in front, we're going to be considering it to be an acid. So again, H means we're going to use that acid naming protocol. Now, notice here you have H and one other element. So that's the only things that are involved in a binary acid compound. So what we do is we do this. The first step says name the element in terms of the root of the second element listed. So we're going to look at Cl. And what I do first is I write down all of the name that is listed on the periodic table. So Cl is the element name of chlorine. Now, the second step says chop off the ending and make the ending IC or IC. So what I'm going to do, I'm going to cross out the ending. I'm going to make that element IC. And so now what I'm going to do down below here is I'm going to have chloric, and I'm going to go to step 3, and it says put the prefix hydro in front of that second element name. So right here we have hydro, chloric, and then the last step is to make sure that's an acid. We just put the word acid behind that. So HCl, when we name it using the acid naming protocol or the binary acid naming protocol, it becomes hydrochloric acid. So now we can move down to H2S. Again, think to ourselves, how do I know it is an acid? Well, that H is out in front. Going through the naming protocol, we always start here when we have an acid with that second element listed, we have an S. And again, I like to look, what is that name of the whole entire element? And that name is sulfur. So we write down our sulfur. The second step is to chop off that ending or modify it to have the IC or IC ending on the end of this element here. Now, like I said, each and every element has a little bit different way it adds or tacks on that IC. And so typically they go with what sounds the best or flows the best when you say it. So for H2S, and we get sulfur, what they do is they actually just tack on that IC ending to the end of the element name sulfur. Now, we go to step 3 after that, which says add the prefix hydro in front of this term that we just named. And so we have hydrosulfuric, and then we have to add the word acid. So what I'm going to do here is I'm going to rewrite hydrosulfuric to make it one word. And then we add the word acid to indicate that it is an acid. So H2S becomes hydrosulfuric acid. So we've learned how to name a binary acid, so an H plus one other element. Now what we're going to do, we're going to throw in our oxyacids. And they're not too much different than the binary acids. We just have to remember really one important thing, and I'll get to it in the steps. So our first step to name an oxyacid is to identify the polyatomic ion that is involved in this particular acid. All right, so just a reminder here, with our polyatomic ions, remember that is a mini atom ion. So how do I know if it's a mini atom ion? Well, you take a look back in the notes from the ionic compounds. Notice here there are mini atom ions that have multiple atoms attached together to have that one ion. So that's how we identify it first. Then the second step is to change the ending of the polyatomic ion form. Now there's two different categories here. The first category changes ATE endings to IC. So to show you that here, I have chlor8. That would change to chloric. The other option is to change the ITE ending to OUS. So to show you that example here, this just below, it's a different ion, chlorite, would change to chloris, that OUS ending. And then the third step here in our oxyacids is to place the word acid after that polyatomic ion is named and modified. Now, notice here that there is no hydro prefix when we name an oxyacid. All right, so let's go ahead and try some examples. So we have HClO3. How do we know it's an acid? Got that H, that hydrogen, out in front. So what we need to do, notice how there is H and a bunch of stuff behind our H. That indicates that that is a polyatomic ion. So what I like to do is I like to just divide this, and then on your ion sheet, we are going to look for ClO3. So we look for ClO3, and ClO3, we find it here. The name is chlor8. So we go ahead and we write that down, chlor8, and then we go to our rules. It says ATE ending changes to IC. So ATE, we cross that out, and this becomes not chlorate, but chloric. And then what we need to do is we need to add the word acid after the particular word. So we just tag that along with acid. And so when we rewrite this, HClO3 becomes just chloric acid. Again, notice how there is no hydro prefix, and that's because you have that polyatomic ion, or H, and a bunch other elements attached with it. So let's go ahead and try it for HCl2. Again, how do I know it's a acid? Ding, ding, ding. That H indicates I have an acid. Now again, I like to divide the H from everything else in this particular acid. And then I have ClO2. So I look on my sheet. If we're not familiar here, ClO2 is given the name of chlorite. So I write down chlorite, and then I look back here. The ITE ending changes to OUS. So what I'm going to do, cross out ITE and tack on OUS. The last step here is just to tag along the word acid. So when I rewrite the name for HClO2, it becomes chlorous acid. Notice too, as I'm writing this, notice too, there is no hydro prefix. And that's because it's H and a bunch other elements after that H. So just be careful there. Okay, so now that we have named named our acids, both types of acid, we named our covalent compounds, now we need to go backwards. We need to go from our names to writing our formulas. So we will shift gears here. So for this, for both acids and covalent compounds, because they are covalent compounds, we can use similar types of steps. So what I've done here is I have just combined these steps together. So the first step to be able to write the formula of a covalent compound or an acid is to find out what or how many atoms we have of each element. And to do this, we just look at the subscripts. So those subscripts are determined from the prefixes in that particular name. So all we'll do is we'll look up the element symbol for each of those names, and then towards the bottom right, we'll tack on the number of atoms indicated by the prefix. It's too easy. Now, a little caveat here for step 2. If we have a formula of the acid, the formula can actually be derived from the name. When we write the formula for an acid, what we have to keep in mind is that the charges of the H+, the hydrogen, has to balance the charges of the polyatomic ion in a very similar fashion that we did back when we named ionic compounds. Okay, so let's put these steps to the test here, and let's name a covalent compound, or write the formula, and then write the formula for an acid. Okay, so we have nitrogen trifluoride. So the first thing that we do is we look up the element symbols for each of these particular elements. So nitrogen, if we look this up, nitrogen is listed right here, and it has the symbol of N. So all I'm going to do here below nitrogen is I'm going to write N, and then I'm going to find our trifluoride. Now, that is a prefix tri, so we just look to fluoride. The symbol for fluoride is F. Okay, so I'm just going to put down F so we know the symbol. And now we go to add the atoms, or the number of atoms in each element. So we start here with nitrogen because it is the first thing listed. And then we look for the prefix. And there is no prefix. But remember, if there's only one of these elements, there is no prefix mono used. So we just have N. Now, because we just have one, remember we leave that subscript blank to indicate that we have one. Then we put our F right next to it, and then we look up the prefix tri. So the prefix tri, if we look on our sheet, indicates that we have 3 atoms. So to indicate 3 atoms of fluoride, what we do is we put a subscript 3 to the bottom right of our element symbol of F. And that is how we write the formula for covalent compounds. Now we get to acids. So how do I know it is an acid? Well, hey, the problem says acid. What I need to do initially here, because we have an acid, is I need to put my H out in front. So what I'm going to do here is I'm going to write H+, because my second step or my second reminder said, hey, I got to balance my H pluses, and this is a 1 plus, just so you know. And then I have to look at sulfuric. Now, a couple of things to indicate here. It is only a single element if you have that prefix hydro. So do you see a prefix hydro? No. That means that we have to look at those polyatomic ions. Now, how do I do this? Well, I got to go back and I got to remember. The IC ending, if we look back on our steps, our IC ending came or originated from an ATE ending. So what I'm going to do is I'm going to get rid of our acid ending, and I'm gonna look for R8. Now, with sulfuric acid, we actually chop off a little bit more, and so we need to not only just look for sulfurate, that's not right, we need to look for sulfate. So if we get our ion sheet out, we look and we find our sulfate right here. And the formula for sulfate is SO4 2 minus. So I write down SO4 2 minus. Now remember, just like in our writing our ionic formulas for an acid, our charges have to cancel out. So what we do, we take the charge number, in this case 2, and that indicates how many H's we need. So we have H2, then we take the charge from H, which is a 1, and the whole SO4 needs 1. And because SO4 only needs 1, we just write SO4. We don't put parentheses and then 1 because we only need 1. We just write this particular formula down. So our formula for sulfuric acid would become H2SO4. All right, so this concludes another episode of Science with Surback. I hope you have enjoyed this and learned something. And as always, subscribe.